Okay, moving along, 10.1b, series. So the second part of 10.1, we have sequences, and now we have series as part of this one. So a few more things to go over in this section. So what is a series? It's indicated sum of all the terms in a sequence. So sum means you're going to add them up. Sometimes you have a finite series. So this is the indicated sum of all the terms in the finite sequence, right? So remember, that's one that has an endpoint. Sometimes you can do it when there's an infinite series where you indicated the sum of all the infinite sequence. Sometimes they want all of them. Sometimes they just want the first number of terms. We'll get to that as well. So if it's a finite sequence, like in here, you can see this part here. You definitely have just certain numbers. If it's infinite, it'll add up and it'll keep adding forever and ever if you're looking for the series. All right. The nth partial sum. So this is just kind of part of it. So this part here just talks about the sum of the first n terms. So they will denote a number of terms and they want the sum of those. Usually we denote that with an s sub n, like that. And then you kind of calculate each term and that they want, and then up to the nth term, and then find the sum of those terms. So add them up. Okay, so it's just some information here that's good to know. So just kind of put this part here, and you can kind of read over it. But this is just good to know stuff when we talk about infinite series. So when we look at this infinite series here, you can see it kind of goes on and on forever and ever. So when we talk about that in terms of a series and adding it up, so a lot of times we say, since an infinite series does not have a finite number of terms, you might assume that an infinite series has no sum s. That's true sometimes for these here, right? If you're going to go on and on and on, then the numbers are going to add up and get larger and larger and larger, and you'll never get an end to it. However, sometimes you do have sums. For instance, when you have, for that to be the case, if you have like fractions or decimals, then you could have a situation. So in this case, to have a fixed sum of s, the sequence must converge to 0. So we talked about converge in 10.1a, that it must approach 0, never quite touch it, but get closer and closer to 0. So it converges on 0. Notice the sequence of partial sums in the infinite series below appears to approach a sum of 0.1 or 1/9, right? So in this case, we had this sequence where you're doing this and you're constantly just adding one more 0 before the 1, then it's just going to keep going and going and going. Eventually, it's going to be 0.111111 or 1/9 here. So in that case, you do kind of have a sum because never going to get any bigger than that. All right, so keep that in mind as we roll through some of these things here, because there's a couple examples of each of them. All right, so first, this one, 5.1a or 5a, we're looking at find the sixth partial sum of this thing here. Okay, so we know that a1 is 8, a sub 1 is 8, and here is our function a sub n is equal to 0.5 a sub n minus 1. N is greater than or equal to 2 because we already have a sub 1 equals 8. So we need to find the 6 terms here. So let's just do 5a over here. And we need to find the 6 terms. Well, we know the first one, a1, is 8. So that's good. So now for a2, remember we're using this whole thing. So it's going to be 0.5, 0.5 times, well, what does this say here? This a to the n minus 1. Remember, that's from yesterday. That's like a recursive formula. So it's basically using the previous term. So that's what we're going to do each time here. So we know that's 0.5 times the previous term, which was 8. So that gives us 4 for the second term. For the third term, a sub 3, it's going to be 0.5 times 4, because we're going to use the previous term, which is 2. Okay, a sub 4 is going to be 0.5 times 2, which is going to be 1. And I'm just going to keep going down here. A sub 5 is going to be 0.5 times 1, which is going to be 0.5. And then a sub 6 is going to be 0.5 times 0.5, right? You're just using the previous term because that's what it says here to do, okay? It's a recursive formula. So now that's going to be 0.025. Okay, so now we kind of just kind of add all of these things up because those are the 6 terms. So 6 partial sum, when we think about it, put it in terms of S sub 6 would equal 8 plus 4 plus 2 plus 1 plus 0.5 plus 0.25. We can add those up, 12, 14, 15, and then 15.75. Basically would be my answer there, okay? All right, let's look on the other one for the 7th term here. So 5b we'll do over here. Okay, so 7th partial sum. So we got to find the 7 terms of this. So we've got a to the n, and we've got this is our function. So we look at the first one here. We're going to go a sub 1 equals 3 times 1 over 10 to the nth power, so to the first power, which is going to be 3 times 1/10, which is going to be 0.03 or 0.3, sorry. Okay. All right. The next one then, a sub 2 would be 3 times 1/10 to the second power, which is 3 times 1 over 100, which is going to be 3/100ths or 0.03. Okay, and you're might start to notice a pattern here. We go to A3, 3 times 1/10 cubed. So that's 3 times 1 over 1,000 or 3/1000ths, which would be 0.003. Okay, so what you kind of notice is that you're starting to notice the hopefully you are, the pattern here. You got 0.3, 0.03, 0.003. So if we kept doing this work, it's going to be the same thing. You're going to get 0.0003 and so on and so forth for the rest of them. So I can kind of just make sure I do that judgment and just know this is what I'm going to do. So S7 would be all of these added up. Now, again, I probably don't need to if I just pay attention to this part right here, where we talked about these types of series right here, because I know it's probably going to end up adding up to 0.333333. So I could add them all up and go 0.3 plus 0.03 plus 0.003, so on and so forth. Or we can kind of just use that idea above and say, well, this, we know this is going to be 0.3 bar, or if you wanted to write it out, 0.3333. Eventually, you're going to bar, it's going to repeat forever. So that would be your answer right here. Okay. So that's one where it's an infinite series that actually has a sum. Okay. So now let's talk about sigma notation. So this is where we start getting some more symbols and stuff in here. So we can just kind of look for any sequence. And you might want to write this down in here, but any sequence, A1, A sub 1, 2, 3, 4, the sum of the first k terms, so they're going to usually denote a term there, is denoted by this stuff here. So you've got the sigma symbol, and then you've got the number on the bottom is n equals 1 usually. That's the lowest one. That's the lower bound of it. In this case, sometimes it's different. And then k is the upper bound. That's what we're going to find the sum of. So that basically means we're going to take the sum of, for all of a sub n, whatever that function is, we're going to do the first term, because that's the first one, all the way up to whatever the k term is here, to the last one. Okay, so it's just another way of writing it and another symbol. And basically you do the same thing. You add up the number of terms they're asking you for. Okay, so again, this might look like this. It says a sub n is written like that, or some people write it like this with sigma to the left and then the K and N to the right. Some people write it above. Just notice the differences. Some people write it above and below right here. Some people write it like this. Both are the same, and we both read those as the summation from N equals 1 to K, or you can say the sum of from N to K of A sub N, okay? So with 6A, we'll kind of go through this one, all these together and look at it. So 6A, this is saying the sum of from N equals 1 to 5, N squared minus 1 over 2. So that means we got to do these 5 terms, okay? So let's go ahead and do that. So here will be 6A. We'll say this is 6A here. We'll kind of go horizontally, so we'll kind of write on all these. So we know we have to take N squared minus 1, and we have to do from 1 to 5. So we have to do 5 terms. So that's going to be equal to N squared minus 1 over 2. Okay, so it'll be 1 squared minus 1 over 2 plus, now we got to do 2. 2 squared minus 1 over 2 plus 3 squared minus 1 over 2 plus 4 squared minus 1 over 2 plus 5 squared minus 1 over 2. So this is what we're doing. We're getting all the terms, and then we'll add them all up. Okay, then we stop at 5 because that was the upper bound, right? That was where we stopped. So now we just kind of add these up. We can go ahead and say, well, I know this is 1 minus 1 is 0 over 2, so that's 0. This one's going to end up being 3 over 2, right? 4 minus 1 is 3 over 2. This one here, 9 minus 1 is 8 over 2 is 4. Right here, you have 16 minus 1 is 15 over 2. And then finally, 25 minus 1, 24 over 2 is 12. Okay, so when we add these up, just, it might be easier, say 1.5, and this is 7.5. So now when we add these up, we can say that we've got 12, 16, and then 16 and 7.5 is 23.5, 1.5, 25. Okay, so I know I have 25 here as my sum. And the other thing I can do to write it is if I want to write it in sigma notation, I'm going to basically go like this, okay, and say I went from 5 to N equals 1, and then my function here, right, was N squared minus 1 over 2 equals 25. Okay, all right, so let's do the next example. Let's do this in black. All right, so let's do 6B here, okay? All right, now 6B is talking about N cubed minus N squared. That's all we're kind of working with here, right? Okay, so now it also is looking at N equals 1, 2, or sorry, this one we're going, the lower bound is 7 and the upper bound is 13. So now we're going from 7 to 13 here. So when I do this one, I'm looking at 7 cubed minus 7 squared plus 8 cubed minus 8 squared plus 9 cubed minus 9 squared plus 10 cubed minus 10 squared. See if I can move all these. Good. Plus 11 cubed minus 11 squared plus 12 cubed minus 12 squared plus finally 13 cubed minus 13 squared. Okay. So when we do the math, I'm going to save that for you. You're going to get 294 plus 448 plus 648 plus 900 plus 1210 plus 1584, so it's a really large number, plus 2028 here, cubing it and then subtracting the square. So when I add all those up, it comes out to 7,112. Okay, so again, another way to write that in sigma notation, I would go here. We're looking at n equals 7 is the lower bound, 13 was the high bound, and then our function here was n cubed minus n squared. Okay, all right, last one. So 6C. So this one, now this one's another tricky one, right? Because now you have 1 is your low bound, infinity is the high bound, and we're going 6 over 10 to the n power. So you might notice already that we're going to have a situation here where you might notice you're going to have 6 over 10 to the first plus 6 over 10 squared. And you might notice this is going to be one of those infinite sums because number one, we're going to a infinite bound, 6 over 10 cubed plus 6 over 10 to the fourth. But because you've got the exponents in the denominator, that's what's happening. So we could kind of write all this out and then, first 5 terms and then just dot, dot, dot saying it's going to go on and on forever. But we also know that when we do this, you're going to get 6 over 10 here, which is 0.6, then 0.6 over 100, so 6 hundredths, 6 thousandths, right? And so on and so forth, just like our examples we did earlier. So again, we know that this is going to approach 0. It's going to be close, but we know that it's going to be 0 point, if we added it all up, 6 is going to eventually rip. I'm going to do one more just because that's not a good number. It's going to repeat, which is eventually 2/3. Okay, so if we were to write this in summation form and sigma notation, we'd say this is n equals 1 to infinity, and it was 6 over 10 to the n power. And it would be 2/3 we get there. Okay, that's how it works. All right, so those are your sequences, nothing to it. And we'll work on that next.